Hello everyone, my name is Kian Smith. I'm a PhD student at Ghent University, more specific the Laboratory for Chemical Technology, and I will shortly present my current research project regarding connecting thermoplastic polymer synthesis with its recycling. So my research presented here revolves around thermoplastic degradation, both through thermal and chemical means, and does help making plastics more ecological. My research focuses on the thermal degradation of commodity polymers such as PMMA and on the development of degradable substitutes such as poly-MMA MDO. However, due to time restraint, we will only focus on the thermal degradation of PMMA. Here, a kinetic Monte Carlo matrix-based model is presented, which is able to connect chemistry both during synthesis and subsequent degradation. The model is able to track specific structural defects, functional groups, and individual monomer sequences. The model gives information on average properties, chain length distributions, average composition, but also macrostructural sequences. The ultimate goal of this research is to increase the understanding of, firstly, the thermal degradation mechanisms of conventional polymers through localization of structural defects and certain functional groups, and secondly, the hydrolysis of biodegradable polymer substitutes through localization of degradable units. As mentioned before, only the thermal degradation of PMMA will be discussed here. As my research is linking the synthesis process to the recycling of PMMA, the description of the free radical polymerization is very important. Modeling FRP is quite challenging due to the occurrence of diffusion limitations on most of the relevant chemical reactions, which require a significant amount of parameters. For the modeling of FRP of MMA, we considered a very basic reaction scheme with initiation, propagation, termination, and transfer to monomer. From the figure below, you can see the importance of the incorporation of diffusion limitations. So red is a simulation with only intrinsic kinetics, black with the incorporation of the gel effect, yellow with the incorporation of the gel effect and the glass effect, and green is a simulation with the incorporation of the gel effect, glass effect, and cage effect, which are respectively diffusional limitations on termination, propagation, and initiator dissociation. As is clear from the figure below, the incorporation of all three effects is necessary to obtain a nice fit with literature data. The effect that has the most influence on the shape of the conversion curve is clearly the gel effect. That's also why the gel effect has been studied intensively throughout the years. Here we have chosen the REFT-LDT method of Johnson, Hall, and Montero to describe our gel effect. The formulas used are shown below, and they introduce a chain length and conversion dependence in the apparent rate coefficients. Here a plot is shown for the FRP of MMA with 4 different reaction conditions. The red line at 90 degrees, the green line at 70 degrees, and then the blue and the black line at 50 degrees, but with different initiator concentrations. On top, you can see the sec trace for the simulation at 50 degrees with the high amount of initiator. And you can see that once the gel effect kicks in around 40% conversion, the sec trace starts to show a sort of bimodality, which is due to the decrease in termination rate, which makes the chains grow bigger. The in situ generated polymer product is then directly degraded in our kinetic Monte Carlo model. For the degradation of PMMA, we consider 6 different reactions that are well documented in literature based on TGA experiments. Degradation of PMMA is known to initiate at 3 different locations in the PMMA backbone. First, the fission at unsaturated chain ends introduced by termination via disproportionation. 2, the fission at head-to-head defects introduced by termination via recombination. And 3, the head-to-tail fission at random bonds throughout the backbone. Once the initiation has happened, usually the PMMA chains unzip, releasing MMA monomers until they eventually terminate with each other, forming the start product. From literature, it is known that PMMA degrades in 3 different stages. First, head-to-head fission occurs, since these bonds are more prone to break when applying heat. Second, the fission at unsaturated chain ends, which is due to formation of an allylic radical, which is also more likely than normal head-to-tail fission. The simulation shown on the right shows the sec trace shifts to lower molar weight due to the chemical nature of the initiation reactions. First, since head-to-head bonds are formed through recombination of two polymer chains, these chains are in general longer than chains terminated via disproportionation or transfer to monomer. And second, since longer polymer chains have more head-to-tail bonds, they have a greater chance to initiate compared to smaller chains. At the bottom, you can see a plot of the actual monomer sequences with a color code. Blue squares are the initiator fragments, red are the head-to-head bonds, purple are the unsaturated chains, yellow are the saturated chain ends, and black are, of course, the MMA units.